So in this video, we're going to talk about parabolic approximations, which is the foundation of Simpson's rule. Instead of using the straight line segments that produced the trapezoids, we can use parabolas to approximate the definite integral of a continuous function. We partition the interval from a to b into n subintervals of equal length delta x, which equals b minus a over n, but this time we require n to be an even number. On each consecutive pair of intervals, we approximate the curve y equals f of x, which is greater than or equal to 0, by a parabola. A typical parabola passed through 3 consecutive points, which are labeled here on the curve. So here we have some curve that we can see in blue, and in this first image, with an n value of 4, that means we're breaking up our subinterval into 4 subintervals, that ends up giving us 2 parabolas. And one of those parabolas is here, and then another parabola is here. And notice that that's not that great of an approximation, but as we increase the number of parabolas, it gets better. So here with n equaling 8, we have 1 parabola, 2 parabolas, 3, and then 4 parabolas. So it's getting a little bit closer to what we want in terms of the area underneath our curve. So how do we compute the area under each parabola y equals ax squared plus bx plus c? By translating, we can assume that the center point of our parabola is at x sub I equals 0. The area under the parabola and above the x-axis is given by the formula s sub I is equal to the definite integral from negative delta x to positive delta x. So what we're doing here is we have this parabola, and the endpoints are based on negative delta x and positive delta x, and we're assuming it's kind of centered at 0. And if it's not, we're translating it so the center or the vertex, or the center of our interval is at 0. And so we have this parabola here, and if we take the antiderivative of that, we get this cubic, and we're evaluating it we're plugging in delta x and negative delta x. So in the next line, we can see when we plug that in, and then when we simplify that long thing, we end up getting 2a times delta x cubed over 3 plus 2 times c times delta x. And then we can factor out delta x over 3, and then we get this expression right here. So down below, we have y sub I minus 1, which is what we get when we plug in negative delta x into our function here for x, which produces this. If I plug in y sub I, we're going to get, or when we evaluate y sub I, we're going to get c, because at that point, the x value is 0. So ax squared and bx become 0, and so we're just left with c. And then if I want to find y sub I plus 1, what I'm doing is I'm taking delta x, and I'm plugging that into my quadratic function, and we get this expression. Now, why do we care about those? Well, if I take the combination y sub I minus 1 plus 4 times y sub I plus y sub I plus 1, that's going to give us this expression here, which simplifies to this, and that's what we saw earlier right here. So, in order to get this, we're basically saying that s sub I is equal to delta x over 3 times y sub I minus 1 plus 4 times y sub I plus y sub I plus 1. So this is kind of where we are getting Simpson's rule from. So let's sum up all the areas under the parabolas, just like we did with trapezoidal rule. So let's call the sum that we're looking for s, and that would be equal to s sub 1 plus s sub 3 plus s sub 5 plus dot 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 plus s of n minus 1. And why are we skipping the even numbers? So if we come back up here, our first parabola is centered at x sub 1, so there's one parabola. Our next one is centered at x sub 3, so there's another parabola, and so on and so forth. And then our last one is centered at n minus 1, which in this case happens to be x sub 7 since our n value is 8. So that's why we have this here. And if we use this formula, s sub I, then s sub 1, if we expand that, that's going to be delta x over 3 times y sub 0 plus 4 y sub 1 plus y sub 2. And then now I want to expand out s sub 3. That is going to be y sub 2 plus 4 y sub 3 plus y sub 4. And then we want to continue this on. And then the very last one is going to be delta x over 3 times y sub n minus 2 plus 4 times y sub n minus 1 plus y sub n. And notice again, kind of like last time when we were doing trapezoidal rule, these all have a delta x over 3, and so we could factor that out. And then what's going to happen is we have y sub 0 plus 4 y sub 1, and then I have a y sub 2 plus a y sub 2, so there's going to be 2 of those. And then we have a 4 y sub 3, and then the y sub 4, there's going to be another y sub 4 there. So are you able to see the pattern? And then notice that there's a 4 y sub n minus 1, and then plus y sub n. So this is essentially the formula for Simpson's rule. So here we have a more formal definition or formal formula for Simpson's rule. The definite integral from a to b of f of x dx is approximately equal to s sub n, which is equal to delta x over 3 times these y values, or the x values where we plug it into the function. And then notice that the pattern is that the first term and the last term both have coefficients of 1. And then what happens is then the coefficients alternate between 4 and 2. So that's the pattern that we're dealing with when we're using Simpson's rule. So example 2 says, use the Simpson's rule with n equals 4 to approximate the definite integral from 0 to 2 of 5x to the 4th dx. Compare the estimate and exact value. So just to reiterate this or emphasize this, our n value has to be even when we're using Simpson's rule. So that's something to keep in mind. Here we have n equals 4, so we're in the clear since 4 is an even number. So we are wanting to evaluate s sub 4. Let's calculate delta x first. So delta x is equal to b minus a over n, which our b value is 2, our a value is 0, and our n value is 4. So this is going to end up equaling 1/2. So we have 1/2 over 3 times f of x sub 0 plus 4 times f of x sub 1 plus 2 times f of x sub 2 plus 4 times f of x sub 3 and then plus f of x sub 4. So let's go ahead and figure out what our x sub i's are. X sub 0 is equal to our a value, which in this case is 0. And then x sub 1 is going to be 1/2. X sub 2 is equal to 1. X sub 3 is equal to 3/2. And then x sub 4 is equal to 2, which is also equal to our b value. Okay, so I went ahead and I expanded out s sub 4. I simplified 1/2 divided by 3 would give us 1/6. And then I went ahead and I plugged in the x sub i's into the f or function notation. Now what I'm going to do is I'm going to take all of these x values and I'm going to plug them into our function f of x equals 5x to the 4th. Okay, so I went ahead and I plugged in those values into my function. Hopefully I did my arithmetic correctly. And let's go ahead and simplify this. This is going to be, if we simplify it all down, it should come out to be 385 over 12. Similar to the previous example, we want to compare the estimate and the exact value. So I'm going to go off and do that to the side here in a different color. So we want to find the exact value of the definite integral from 0 to 2 of 5x to the 4th power dx. The antiderivative of that is going to be x to the 5th power, and we're evaluating this from x equals 0 to x equals 2. And that's going to be 2 to the 5th minus 0 to the 5th, which is going to end up equaling 32. And so we want to compare the results, so let's subtract. So I went ahead and I did the comparison. Here is our approximation using S sub 4, and this is our exact value. And so our approximation is 1/12 larger than our exact value, which isn't terrible. If you use an approximation technique, it's important to know how accurate you can expect the approximation to be. This process is called error analysis. The error in using an approximation is defined to be the amount that needs to be added to the approximation to make it exact. In other words, the definite integral from a to b of f of x dx is equal to the approximation plus its error. We generally care about the magnitude of the error and measure it in two ways. Those two ways are absolute error, which is equal to the absolute value of the exact value minus the approximation. And then the other kind of error we care about is called relative error, and that's equal to the absolute value of the exact value minus the approximation divided by the exact value. The irony is that to find the error, you must know the exact answer, but if you have the exact answer, why would you be seeking an approximation in the first place? Well, in application, perhaps as an engineer or applied mathematician, you will use approximation techniques in situations where you do not know the exact answer. However, for these approximations to be valuable, you must know something about their accuracy. This leads us to the concept of an error bound. So next we'll talk about error estimates in the trapezoidal and Simpson's rule. If our second derivative of f is continuous and the absolute value of the second derivative is less than or equal to some capital M on the closed interval from a to b, then the error e sub t in the trapezoidal rule for approximating the definite integral of f of x over the closed interval from a to b using n trapezoids satisfies the inequality. The absolute value of e sub t is less than or equal to capital M times b minus a cubed over 12 times n squared. If the fourth derivative of f of x is continuous and the absolute value of the fourth derivative of f of x is less than or equal to capital M on the closed interval from a to b, then the error e sub s in Simpson's rule for approximating the definite integral of f of x over the interval from a to b using n over 2 parabolas satisfies the inequality. The absolute value of e sub s is less than or equal to capital M times b minus a to the 5th power over 180 times n to the 4th power. In the above two inequalities, capital M is called an upper bound. Let's put this into practice. Example 3 says, find an upper bound for the error in estimating the definite integral from 0 to 2 of 5x to the 4th power dx using Simpson's rule with n equal to 4. What value of n should we pick so that the error is within 0.001 of the true value? So if you remember from the purple box just a moment ago, we are trying to find an upper bound if we're using Simpson's rule for the fourth derivative of x. And we want that to be less than or equal to some value for capital N. So the way that we're going to start this off is we're going to find the fourth derivative of our function. So if our function f of x in this case is 5x to the 4th power, let's go ahead and find some derivatives. So f prime of x is equal to 20x cubed. F double prime of x is equal to 60x squared. F triple prime of x is equal to 120x. And then our 4th derivative, finally, is equal to 120. And so in this particular instance, our 4th derivative, if we take the absolute value of it, is less than or equal to the number 120. So notice that this is a constant, so our 4th derivative is always going to be less than or equal to 120. And so in this case, our upper bound, capital M, is equal to 120. So again, from the purple box just moments ago, we were given that the absolute value of the error for Simpson's rule is less than or equal to capital M times B minus A to the 5th power over 180 times n to the 4th power. And we have values for these, so our upper bound is 120. B minus A is 2 minus 0, which is 2 to the 5th power. And then we have 180 times our given n value is n equals 4, so I have 4 to the 4th power. And if you simplify this number, this ends up equaling 1 over 12. And that's really nice because what that says is if you use Simpson's rule and you use n equals 4, which is with 2 parabolas, that means that the most that the error is going to be is 1/12 off, which that was the case. It was exactly 1/12 off when we made our calculation. So this is really nice that we have this inequality because, again, if you go off into something like aerospace engineering or something like that, you need to know how off your error is going to be for the approximate or the approximation that you would be calculating from the actual or exact answer. And the second part of this question says, what value of n should we pick so that the error is within 0.001 of the true value? So unfortunately, using an n value of 4 would give us an error of 1/12, which might not be satisfying some stringent requirements that like NASA has or something like that. So maybe you work for NASA and they have really stringent requirements in terms of how off your error can be. And so maybe they need you to be within 0.001 of the true value. So how do we figure out what our n value should be so that it is close enough to the true value? Well, essentially what we're doing is we're taking this thing here because we have the capital M, the B, and the A value, and we're just filling back in the lowercase n, and ultimately we're going to set up an inequality and then solve it for n. So let's do that. I'm just going to copy that circled thing down. So I've gone ahead and I've rewritten that fraction, except now we have n in place of 4 since we want to know how many subintervals we need to get so that our answer is accurate enough, or more specifically within 0.001 of the true value. So we want to set this less than or equal to 0.001. And now we're solving this inequality for n. I'm going to clean up the screen a little bit. Okay, so 120 divided by 180, I can divide both of those by 10, and then we have 12 over 18, which simplifies to 2 over 3. So then that would give us 2 to the 6th power over 3n to the 4th power is less than or equal to 0.001. And now we want to solve this inequality for n. So I'm going to multiply both sides by n to the 4th power. So that's going to give me 0.001 n to the fourth power is greater than or equal to 2 to the sixth over 3. And then I can divide both sides by 0.001. That's going to give me n to the fourth is greater than or equal to 2 to the sixth. Dividing by 0.001 is the same thing as multiplying by 1000. And so now we can take the fourth root. So n is greater than or equal to the fourth root of 2 to the sixth times 1000 divided by 3. And if you have a calculator, this is approximately equal to 12.086. So let's write a sentence. We need n to be greater than or equal to 12.086 so that our error is within 0.001 of the true value. And remember, n has to be even, and so really the smallest n could actually be, because we also need n to be an integer, is going to be 14, since 12 wouldn't work because it's not larger than this decimal here.